All right. So I extended the coding assignment A1 deadline. Am I? No. Is it better? Yes. Extended deadline because I totally forgot it's the long weekend and you probably not work. So pay attention to the deadline. I think I made it due by the class time, right? Let's check that out. Make sure everybody knows. It's here. Yes. September 8th. Class time. So beginning of class. So don't leave it for the last like 2:59. So I reviewed the fishbowl survey from last week. This week I have different classes for the students. So I'll get back on my track soon and find my routines. But from so today we're gonna review things that you guys told me and girls on there, and also things from last week. So nothing new. We're gonna finish everything up, send you to the long weekend, and come back next week fresh, so we can continue. And we will work with vacation next week. So hopefully, if you think that you need to work on this long weekend, maybe a good time for that. One of you said that the video doesn't capture my voice very well, and as I told you before, I'm recording this just as a supplementary material. This is an in-person class. Now, if you didn't understand something that I said, first of all, the mask doesn't let you to see my lips, and I have an accent, so things might not be clear. Don't worry, I'm aware of that. That's why there's me using Discord. Type in the chat, hey, I didn't get what she said about this. Either Brett will answer you or someone here, they will. Now, someone asked why we're using Discord, not using Carmen discussion, why we have to open many softwares. First of all, all of us open many software in Windows. So that I don't think is anything uncomfortable. Second, based on my experience, students don't like Carmen discussion for some reason. You know, Discord is more like, I don't know, everyday thing, and you don't have to only use it during the class time. You can talk to each other. You can post cool things there. And I feel like it's kind of like a tool for you to keep in touch outside of the classroom, especially when we get to assignments, coding, topics that are not familiar to a lot of you. That's a fine place to discuss because both me and your TA are present and can see the discussion. All right. So I'm sorry if it is if it's not very convenient, but I think it will have a better result if you use Discord instead of this Carmen discussion. And also for my mental health, because during COVID and virtual teaching, we're always using Carmen discussion, so I'm just taking a break from it. All right. Feel free to always ask questions. Come to my office hours, shoot me an email. I reply pretty quickly if I see your email. So those two are kind of related, but not related to the technical aspect of the classroom. Sound good? So have your Discord ready. You come into the classroom, have Carmen open, have Discord open. That's your things to do before classroom. All right. Now, some of you asked me where we can find the stuff. Again, every week we have modules. So this is probably last time I will repeat it. So this is probably not going to show on Zoom, but you know, if you go to modules, the week that we are in, and there is date at the end of this lecture material, so exactly know where we are, click it in here. You'll see the blank lecture. If it is something in the past, for example, you wanted to check out Wednesdays, can go here. Oh, no, that's the CP. Here under lecture. You go here, you see the annotated version, you also see the recording. Again, this might not capture everything. You see, I walk around a lot. So whatever this mic captures, or if I'm here and writing something, all right? So feel free to ask your question in Discord. Now, let's go and start. Any question about logistics in general? Any questions? Okay. Whenever you don't feel it, you talk, just step in. All right. Okay, everybody sees this. No. So I think, so these are the topics that I decided to discuss from Fishbowl. I think I made a mistake here on this example, and a couple of you mentioned, and I continue to correct it. So I made a mistake here. So let's do this together again. Internet is not stable. All right. So this is the same manipulator. We are looking at two different angles, right? So erase whatever I said before. That's a blank slate. We want to find state state. Now, I explained that state space. Now here we are just thinking about the state space in manipulator. So you remember that we discussed about joint variables, right? Anybody remember what joint variable is? Yes, Cam? Yes, how many joints you have? Like what joints that have, like, and then we can find the position and velocity. So those are our variables. That's what we call joint variable. Now, state space is a combination of the joint variable and their velocity, right? So now in this specific example, from the side view, this robot has two joints. Now I'm gonna show the links so you'll see that there are made mistakes. And I think most of you were right. So from this side, it looks like this is a valve. That's what I thought it was. So on this view, we have a theta 1 here and a theta 2, right? Two joints. These are going to be a joint part of our joint variables. Now, if we go to top view, I'm going to show those links and the red one. So I didn't pay attention to this. That showed the motion. So this red, so this last is also a joint variable. So now, usually we number them like this. Theta 1, 2, 3, because we want to start from the base and go. All right. But if you want to just think about how many joints we have, this has 3 joints. From the 2D, we couldn't see all of it. But from this gray area, I should have noticed, I should have realized this is a third joint because we can go here, right? Move in this direction. That's what the gray area is telling us. Move in this direction. For here, since we are not moving in this direction, this only moves, for example, here, or it can move here. That's why the gray area looks like that. All right. So we have 3 joints. All of them are revolute joints. So our speed space, we have theta 1, 2, and theta 3. Then we have the velocities, theta dot 1, theta dot 2, theta dot 3. We can use these 6 variables. So this is a vector, right? So we can use these to tell future of our robot, of our robot at any time. We can know the location, what the velocity, what the acceleration. Now, if we wanted, for example, also do some make some calculations, calculate the forces, it will be added to our space state, right? But we are not concerned about that yet. So depending on what you're trying to solve, your state space can change. So state is where your robot is expected to at all times, right? Now, the state is that there. The state is the element of the machine. Now, if you were thinking about force, it will be added to the state. So, I don't know if you answer that question, right? About acceleration. Yeah. So, really depending on what you're trying to solve, our state and state can and be more than this. For us, we are only looking for position and velocity now. Okay. So, is this clear? Okay, so I'm sorry if I made a mistake. I didn't listen. Then I check this clear. Many of you if more than 3 are saying, oh, John, I'm wrong. So I checked it again. There were questions about degree of freedom. Hopefully, so this was from week 1. Hopefully, with the examples that you saw, or clarify. If it's not, whenever we have an example, please discuss about it and let me know. Configuration of space and join variable. So I talked about join variable, but there was a question about what if we have a P or P, for example? How are we going to show the state variable for this? Well, we don't exactly know. So if I just say P or P, the only thing you know is that there's a prismatic, revolute, and prismatic. You really don't know how they are configured. So you can't represent any configuration. You can just say that, okay, this is a PRP join. All the information you have is 3 joins. You're gonna have probably D1, D1, theta2, D2, D.1, theta3, theta2, D.3. State space. That's the only information you can get if I don't show you anything else. All right, so you cannot really represent anything. You can't just say that, okay, this is, because it could be different configurations depending on the z-axis, right? You learn that. So you can't really say what this robot is. Did you figure out the Cartesian? Yeah. Okay. All right. So I think these were the muddiest point that I picked up from the surveys. If there's something that I didn't, feel free to put in this week's fishbowl so I can go back to it again. Sounds good? Awesome. All right, so I asked you on Wednesday to work on this. Please, if you have done this, please bring it up so I can see. If not, I want you to spend maybe about 2 to 3 minutes to find M, N, and J. And like, what's your approach? I'm going to go walk around and then I'll solve it. All right. If you have done it, show me the degree of freedom that you found. So I want to discuss. This is the equation, the Gaussian equation for the using crystal, and also the table. Like how many you want to have how many crystals. It will help you when you're trying to find the duration. But it's the quantity of water. Remember 50. If you were 51 too. Yeah. So what this robot will say this is base. How do you think this is basic of platform, right? Like put something here. How do you think this moves? And then check if 15 makes sense and matches. Like you have 15 for that. And if it's 15, why do you got that? Thank you. Yeah. It seems like you have to. Yeah. So I'll show you a way to show it. Doesn't matter. It doesn't matter. That's why I chose this example. I wanted to break on the. If there's a. Yes. And tell you have to why you got that. What? That was the problem.
So if account even in the example,
So what is M? 6, you all agree? This is in 3D, right? Let me, I'm also using memory buffer.
So that's how I got 51, like each of those ones. Or you're talking about, no, each of those would be so like Except for the ones on top. That should
Let's see.
this one bar with this third like full down and just rotate in place. Yeah. So it rotates like you can have this effect on the stage and then have that on the kind of very helpful, but it should still be I mean, that's my logic behind not this rotation. I mean, let's say this thing was just a bar, it was a bar that was kind of cute, I kept it sticking out, then it was very drastically disoriented. Because then it was trying to be able to fit somewhere. But that's what the same time they went there. It would be if all
All right, I want you to fill in the blanks. All right, so this mechanism has a base. So this could be attached to anything. This is a Delta robot. And you have a top platform that you can put things on, move, but that's the part that's actually moving. So now this, if you think of it now, this mechanism as there's a base and there's a top platform, you can think of these structures as 3 legs. Now you can think this goes up and down, right? Then you have bends here, or you can also rotate, right? Now, each leg, how many links each leg has? So some of you might have miscounted because it doesn't look very, it's not very clear how many links you have. Let's count together. So this is one, oh, let me change the color. I like colors. 1 link. So this one, this is a revolute joint that revolutes on 1 link. So this is not 2 different links here. It wouldn't make sense like for them to be separate. But if it was, you'll probably be told. So this is another link. That's the part that some of you might have made a mistake counting those. This is 1 link, same thing here, another link. So let's say 1, 2, 3, 4, 5. So each leg has 5 links. Now let's see how many joints they have. How many spherical joints they have in each of these legs? 4. 1, 2, 3, 4. How many revolute joints they have? 3. Now we can put this mechanism back together, right? So these are all rigid bodies. They have their own freedom. They're allowed to put them back, right? So what is N? We have 3 robots, 3 legs, sorry, times 5 links plus your top platform plus base. I just call them platform and base so it's easier to see what's happening. So this is 17, right? If you got 17, you're halfway there. Now, number of joints, 3 times we have 4 spherical plus 3 revolute. What's this number? 21. So we have 21 joints. Now to find sigma fi, it's always very good to go this way because now this is very easy, right? You're not going to make a mistake. So that is another place that you can get trapped and make a mistake. So this is 3 times 4 times 3 plus 3 times 1. What's this? What you get? 46. Okay, I need to do myself. 45, yeah, 45 sounds about right. Now DOF is 6 times, remember, we are in m equal to 6, right? Let me write it. Also different colors, because I like colors. So 6 times n 17 minus 1 minus 21 plus 45. This gives you 15, right? Now, if you think about it, this top platform, how many degrees of freedom actually the top platform are? Forget about this 15. How does this move? Like, what are the goes up and down, back and forth, right? Might be able to tilt it too. Let's say, I think it's 3, but let's say 6. Like, let's say it can be suspended in the space, right? So there is a difference. What are those? Why we have 15 instead of 6? Those are, yes.
The same orientation when the wings are in different spots. Like
Yes.
either candidate.
Yeah, so they're called idle degree of freedom. IW, the difference. Because if you look, so those degree of freedom is for the structure itself. It does not contribute to the degree of freedom of the whole mechanism. So this is a spherical. That's a spherical. It means that if there was a link, this could move around itself, right? Rotate around its own axis. So it gives, so this idle degree of freedom gives you the degree of freedom. Think about motion, freedom of motion to the structure itself. But as this mechanism, total, your mechanism has a lot less degree of freedom. That's why I'm a human. I'm doing this space. I must have 6 maximum. But even if you count from here to here, you probably find 14 at least degree of freedom. These are the freedom of motion that this mechanism itself. All right. So if I can stay here and move my wrist, right? I can also move my elbow, but if the elbow is not moving, it's coming from my shoulder actually, right? So I could either move my shoulder to reach that, or if I'm really good at this, I can just move my wrist and get the same motion. So if you happen to get the degree of freedom very large, and you said that, oh, I should be thinking this seems wrong. It might not be. It is because of the mechanism. You have to go and check the mechanism. If you ever design something, there are other aspects that your system has to have that causes that extra. I want to say take it with grain of salt. I'm going to say freedom of motion, but that might help you better. Like you can move this arm. Maybe you needed to clean this arm. You had a system that will add oil. This is in the space. And once you add oil, you need to rotate this to maintain itself. So it does something else. It doesn't contribute directly to the position of the platform. Make sense? Okay. So this example, there are 2 reasons that I brought it. One, for you to see the difference. Second, this is something really you never saw in 3D. So with the combination of all the 2D examples and this 3D example, I think you should be good. If you see something, at least you should be able to find numbers and think, does this make sense? I always want you for anything in this class, when you find an answer, always think, does this make sense? If it didn't, go back, ask me, or if it's like an exam, write that this number doesn't make sense. I think my calculation's right, and tell me what. So if your train of thought is correct, you're not going to lose too much points. Yes.
On a robot leg, you explain why if there's just one link between SR and
Here,
SO2.
so look at this. This is that rod, and this is the R joint. This can move. It's not 2 pieces, it's 1 piece. Here. That's the part that I thought some of you may have made a mistake. Not as 2. If you count as 2, then you get the because it. Right, so this is 1. So these are in my experience about idle degree of freedom. I wrote it better. So the remaining are idle DOFs. Okay, back to the sweet rotation matrix. All right. I'll give you 5 minutes to find the rotation matrix. Don't look at the annotated version. Try to find it yourself. All right, and then I'll solve it. I know you had questions, so you can ask me then. I don't know, when I emailed you, if you get what I meant or not. But here, if you didn't understand, you can call me, ask me that. Right? Do you have a question? Anything going on there? For some reason, I think Delta has only 3 years again, but yeah, let's see. Wait a second. You can use the direction cosine method or projection method, whichever you're more comfortable with. Okay, yeah. Okay, so think about which one will you choose. With this, we can actually just do that. Show me how it goes. Like in the exam, we don't find the hard one. So in the exam, you have to show me your work, not to show me the final solution, because you could just be lucky, like be lucky. So where are you using this? So I want you to on your left use the audio one product. Okay, because then so this is your final product. Since we're using that right now, I want you to use the God product. Copy paste that here. Yeah, but this is it has to be with this one. Sometimes the location is not on that. And you want to do it. So what I'm going to do is I'm going to show you one axis at a time. So this would be a good slide to always go back to. So we want to find RAB. So the first one is our original frame. The second one is our new frame, right? So let's draw our original frame. XA, YA, ZA, right? And then we know that from dot product, we are going to find the projection or the dot product of our new axis X on the other three previous axes, right? So our xb dot xa, xb dot ya, and x of b dot za. So far, so good, right? So the first. Now, what does it mean on the axis? Let's just look at it. So your x of b is in this section, right? This is the quickest way that you can visually also confirm if your solution is correct. Now, one of you asked if this means this is 90 degree probability. Yes, it is. I didn't write, but that's 90 degrees. So now here, if we look at that, so this is 90 degrees. xp dot xa, the projection, what's the one, right? Xp is in the direction of xa, so the angle is 0, cosine 0 is 1, and then these are unity vectors, 1 times 1 is 1. So this is going to be 1. xp dot ya, so this is xp, this is ya. What's the projection? We are building a 90 degree angle at 0. xp and za, same thing. So this is very quick. If you forgot or if it's more difficult to visualize how it works when using the dot product, so these are different methods, you can put them all together. And once you do it a couple of times, so this week, next week, it might be a little bit difficult, but then we're going to do so many times that when you see it, you know exactly what. All right. So don't be too hard on yourself if you don't get it the first time. All right. So now the second one, and now we're going to go on y of b. We're going to project y of b on xa, ya, za. All right. Same thing. I'm going to draw one more, and then after that, just put the third one. So this is your ya, xa, za, and let's see where is our yb. Yb is in this direction. Now it's very clear, right? So you have 1 in one direction, 0s in the other directions. So 0 on x and y and here. And then you have zb, zb dot xa, ya, za. All right, so what's the solution here? Yes. Yes. A -1 is because z is in the negative direction of the positive direction of ya, right? So if you were going to draw that, it would be in the negative direction. So your RAB is 1, 0, 0, 0, 0, 1, 0, -0. Now, if you remember from last class, so all of these annotated versions will be posted right after the class. So don't worry about if you missed something on writing. Okay, understanding and listening is a lot more important. And trust me, if you're taking a nap, you're tired, and you want to go back to it, they might not make sense because I'm not there. My slides are prepared with me in part of it, you know. So I'm not typing everything that I'm saying. So if you remember from last class, I gave you this basic rotation matrix. Basic rotation matrix, you have 3 of them, around X, around Y, around Z. If you look at them, you'll see that this doesn't look like any of them. And the reason is, a lot of time rotations are not just around one axis, they're a combination of rotation on different axes. All right. So you can't just try to figure out what axis this is rotated around, let me use what I have. So that's why you have to be comfortable calculating this. Next week, we will learn how to deal with consecutive rotations. But a lot of time it's very difficult to visualize. The good example is our next example for that. Well, this is your class participation. What's the solution here? Does anybody remember? So you have cosine of theta, right? Sine of theta, 0, negative sine of theta, cosine of theta, 0, 0, 1, 0, 1. This is rotation on z-axis. You could use what you have developed. Now, if you plug in the numbers, 0.7, 0.7, 0, negative 0.7, 7, 0, 0, 0, 1. So that is the solution. So nothing hard, just to try to deal with it. This is the rotation. You went from frame 0 to frame 1. Theta is 45. You want to find the rotation matrix. This is more than one rotation. Okay, you can, if you are very training, you can find what those rotations are, but based on time. Just use the projection method and find the rotation. It will be, you will have one matrix, yes. So instead of doing that, my suggestion is find the rotation matrix and then try to see if you can find what rotation are. So find the rotation matrix based on the dot product or projection method. Okay, and then from there, you'll work see if you can figure out what rotation is. This shouldn't be difficult because instead of moving 90, this moves 45. All right, so for you to solve, it is 45 instead of 90, yes. Okay, so I'm going to show you what was the, because yes, this is in 3D, shown on 2D, not the best. So this is it, this was your original frame, okay? And then if you think of this as the plane of x0, z0 axes, this is your y1. And this is your x1. So hopefully they will, I mean, it's drawn there too, but it doesn't show very well. I don't know for some reason. And this is your z1. Always 90 degree orthogonal. Yes, so what's the problem with that? So this was your original axis. Some rotation happened, now it's like this. Okay, you don't know what happened here. You know that at the end, the angle between x1 and x0 is 45. That's why I'm asking you, instead of visualizing, start using the projection cosine. Okay, then we'll find the solution. One. Did anybody find this column? This one? Okay. So let's look at this. So the first one, did you get the first one? All right, what is this, the one in the middle? No, backward. So y1, right? So this one here, if this is 45, then this is also 45, right? Okay. So on x, this is cosine of 45. Then you have 0 projection on y0, and on z, you are in the negative side of z0. That is sine of that angle, negative sine of 45. Now, you'll be lucky because sine and cosine are the same. You find solution, that's why you have to come here. And then now, how about the third row, the third column? This one, z1 is in direction of y0. That's easy, right? So direction of 0, 1, 0. Good. This is a rotation by 90 degree, and then a rotation around the new axis by negative 45. Next week, we will learn about consistent rotation. It is important how we rotate. So we can go back to this example and see. Yes. This is the R01. This is the rotation matrix. So your rotation matrix is it this? Okay, so this is important because if we had an object in the previous frame and had it XYZ and we rotate to this new frame, we wanted to find their position, then we can pre-multiply this rotation matrix by the position, the original position, and it give us the position. And that's why, and then so you calculate once and you can't find any position or velocity for that matter from the original frame to your new frame. Thinking you have a camera, you have a car, you know what's the rotation matrix, the car moves, you can tell what is exactly the position from camera's point of view at any time. So car and camera can talk to each other and exactly both talk about the same position. Okay, so there's one rotation matrix always in the loop. Again, the solution will be uploaded as soon as you're done here. So this 3 rotation, basic rotation, you might sometimes see this as rotation z theta. It's the same as if you say RZ and theta. Same for X and Y. These are 2 properties of rotation matrix. Rotation around z axis for 0 degree. What's the rotation matrix? If you're rotating around your z axis for 0 degree, what's the rotation matrix? Identity, right? Or 1. So you will never say 0 because then everything is 0. So If no rotation happens, it's 1. All right. You can also, if rotation are around the same axis, you can add them. So if this was my z, I'm rotating theta, then I'm rotating around the same another c. The full rotation is theta plus b. We'll talk about this later Wednesday when we come back. One thing I want you guys to think about is using this property RZ and theta inverse is equal RZ and negative theta. All right. Using this property, I want you to show me R transpose is equal to R inverse. Use rotation matrix in R2. So you have something to work with. This is just a food for thought. There's no assignment for it, but work on this and show me when next time class. And talk about it. We should be able to prove this. And we use this a lot. All right. Right on the dot. So I'm done. There is a class participation. It's kind of the same as the last class participation. It's not difficult. If you need to build your own VX, Y, Z axis and be able to move around, there is our stuff here. Come and take them. No.